So welcome once again to week 2. Here we are with Chemistry of Life, part 1, just the first half of this chapter. And our introduction to elements, atoms, and isotopes, oh my. So once again, we're just recovering a little bit of basic chemistry. And to give you an idea about this chapter, once again, I know I already covered it in my other introduction, but I thought I'd mention a few things. This chapter we are going to, once again, as you can see, cover elements, atoms, isotopes. We want to cover basic chemistry and how it relates to life, how it relates to biology. So also we're going to take some time and talk about water. Now, in addition to the unique properties of water that we're going to discuss that are important to life, next week's module we're really going to dig into those 4 big biological molecules that I had mentioned in the introduction, which once again were carbohydrates, proteins, lipids, and nucleic acids. Now, why am I bringing this up all over again, being that you probably just watched the introduction video? Because these 4 big biological molecules, as well as water, are going to come up again and again and again in biology. Everything from the cellular level to the organ system level. So we have to have a decent understanding of basic chemistry, and specifically the chemistry of water, carbohydrates, proteins, lipids, and nucleic acid to really understand what's going on. So that's what we're covering. So once again, the general chemistry view, atoms and molecules, basic bonding, how molecules are formed from atoms, water and living things, the formation and destruction of covalent bonds. All right, and getting into that's related to the molecules of life, those 4 big molecules, and the synthesis of those polymers. So let's go ahead and get started. And once again, why is it important? For exactly the same reason I've already discussed. What right now we're discussing right down here, the atomic and molecular level, because it sets the foundation for all of life, which once again, life starts from here up at the cellular level. We're going to talk more about cytology in 2 weeks when we get into chapter 3, the cell theory, but basically all life is based around this concept of the cell, and cells are made up of molecules. So atoms and molecules, some basic science I'm sure you've probably had before in previous schooling, and just basic definitions. So matter is anything that has weight and takes up space. So anything that is in physical existence is made up of matter. And the basic building blocks of matter that cannot be broken down by chemical means, gotta be stressed about that, cannot be broken down at all by chemical means, those are elements. Those are the basic building blocks of all matter. And atoms are the smallest units of an element. So when we're going to look at the periodic table, we're going to look at the periodic table of elements, and the smallest unit of a particular element are atoms. And atoms, once again, the smallest units of an element that retain the element's physical and chemical properties. And atoms, once again, come together to form molecules. So these are basic definitions. Let's kind of make them a little bit more practical now. What makes up an atom? That's what we're talking about here with subatomic particles. And there are 3 that we're going to be concerned with, at least. Physicists and chemists can imagine about breaking them down more, but we're going to talk about these subatomic particles. The first one being the proton. And the proton is located in the nucleus of an atom, and it has a single positive charge. And it has a mass of approximately 1 AMU, which is an atomic mass unit. Once again, contained in the nucleus. And when we look at an element in the periodic table, we're going to see that they're all based around their atomic number. And their atomic number is the number of protons in an atom of that element. So when we define our elements by their atomic number, we define our elements by the number of protons they have. Then we have neutrons, once again, located in the nucleus of an atom, and they are technically slightly larger than a proton, but they carry no charge. All right, so up here With the proton, we have a positive charge and approximately 1 atomic mass unit. Here, once again, zero charge and pretty much the same size. Okay? So different isotopes of an element, and this is going to be a key term that we're going to talk about a lot in this little mini lecture here, have different numbers of neutrons but the same number of protons. So if we can imagine, once again, if I imagine a little nucleus here, and we have 1 proton, we're going to find out that that's going to define hydrogen. And typically hydrogen actually will not have a neutron along with it. It's a little bit unique that way. But if we throw a proton with a neutron in there, it's an isotope of hydrogen now. Still hydrogen because, once again, elements are defined by the number of protons they have. It's still hydrogen, but it's an isotope because we've doubled the mass, because these things are pretty much have the same amount of mass. Okay? So the mass number that we're going to see on the periodic table is equal to the number of protons and neutrons, adding them up together. So the mass number right here in this example would be 1, but the mass number of this isotope of hydrogen would be 2. And we'll get into what that really means in a little bit. On the periodic table, the element is designated by a large capital letter, sometimes a capital and a smaller lowercase level letter as well. So there's a shorthand notation for it. Often it will be the first letter of the element, but sometimes it won't be. Sometimes it'll be back to their Latin or Greek roots, like, for example, iron is Fe, going back to, I believe, the Latin for iron, ferrous. The atomic number, which really, once again, is defining it, the number of protons, represented, but once again, by Z here, and the mass number will be on top. Okay? And now here we get to those electrons. So electrons have a charge equal in magnitude but opposite in sign. So electrons are negative. However, unlike protons and neutrons, they have a very small mass, approximately 1/1837th of a proton. Much, much smaller. All right? So they're much, much smaller, but they're equal in magnitude, opposite in charge. So once again, we call these negatives. Now, they go around the nucleus in these valence electrons. And this, of course, kind of a classical, old school example of an atom. They really don't look like this. And in fact, and the nucleus would be much, much smaller than what's represented here. But they do travel in these orbitals around the nucleus of an electron, of an atom. And electrons farthest from the nucleus are called valence electrons. What we're going to find out is that these electrons travel in these shells, these orbitals around it, and the outermost orbital, the outermost shell, if you will, are called valence electrons. Now, the farther the valence electrons are from the nucleus, the weaker the attractive force between the positively charged nucleus from the protons, and the more likely these outer valence electrons, the outside electrons, will be influenced by other atoms. And this is an important concept. It's the outer shell electrons, these valence electrons, that's going to actually have all the reactivity. So I just threw a lot at you. But the whole concept here is that atoms would like to have the best of both worlds. There's two things that atoms are really looking for. They would like to be neutral, okay, where the number of electrons equals the number of protons, all right? However, even more so than that, they would like to have a complete outer shell of valence electrons. So there's two things they're looking for. Number one, they would like to have a complete outer shell, so valence, of electrons. That's my little symbol for electrons here. Get used to it because you'll be using it a lot. And they would ideally also like to be neutral. But it won't always happen. So in other words, positive equals the negative, right? So what will happen is that in order to get a complete outer shell of valence electrons, two things will happen. Either two atoms will come together and form a molecule by sharing their outer shell of electrons, and that way they complete their each individual's outer shell. Or, as you can see from here, positive or negative charge on an atom is due to a loss or gain of electrons, in which case one atom will pass its outer shell electrons to the other, so they will both have a complete outer shell, but now they're no longer atoms, they're technically ions. They now have either a positive or a negative charge. So here are those elements on the periodic table, and once again, here are the atomic symbols. Here's hydrogen, here's helium over here. I guess I could underline as I talk. So once again, here's hydrogen, here's helium, and then we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and so forth. Now this is obviously, if you've ever seen a periodic table, this is not the complete periodic table of elements. This is just a abridged version, if you will. But I wanted to point out a couple things. Once again, here's our atomic symbol. Here's our atomic number, our Z number, like I mentioned before, up above. And here is our mass number down below. And you notice, other than hydrogen, when we look from our atomic number down to our mass number, usually it's about double, not always quite. Now, when we see the atomic mass down here, what we're doing is we're looking at the atomic mass, how it's typically found on Earth with all the various isotopes. And we typically relate it back down here to what we find as carbon, carbon-12. So carbon typically is found with, obviously it's always going to have 6 protons because that's what defines it as carbon, and typically found also with 6 neutrons, which would give atomic mass of 12. Not always though. Sometimes there are isotopes of carbon which will make it, slightly larger. Which case, if we take an average altogether, the average atomic mass of carbon found is 12.01. Now, once again, if we're visualizing these things, kind of once again a quick summary of everything we just said. Neutrons, once again, have a neutral charge. Protons have a positive charge, and they're both found in the nucleus. So I look at hydrogen. Hydrogen does not have a neutron, so it has 1 proton. So it would have 1 proton here, and an atom of hydrogen would have 1 electron. Electrons, once again, are negatively charged and orbit around the nucleus. Now, a couple things here. Here we are looking at the atoms, okay? But they're never found this way. They're never found with just, in this case, one electron in its outer shell for hydrogen, or 4 for carbon, or 5 for nitrogen, or 6 for oxygen. What's going to want to happen is that each one of these are going to want to fill their outer shell. And I should stop here and mention that the innermost shell of the elements that we're going to be concerned about are going to want to have 2 electrons. So hydrogen only wants 2 electrons because it only has this 1 shell here. But then outside from that, when we move farther out, the shells want 8. Okay, so that's why we're going to say they want a complete octet of electrons in their outermost shell, the valence shell. So we can see that carbon would love to have 8 electrons here, but it only has 4. Nitrogen would like to have 8 electrons in its outermost shell, but it only has 5. And oxygen would love to have 8 electrons in its outermost shell, but it only has 6. So what are we going to do? Well, we need more electrons. But if we randomly add 4 electrons to this carbon, then we'd have this like a -4 charge. Or if we took away the 4 here, so now we leave it down to this lower shell, well, then we'd only have 2 electrons and we'd have 6 protons, then we'd have a +4 charge. It won't like to do that. So what we're going to find is that carbon is going to like to share electrons with other atoms in order to get its octet of 8. So this one's going to like to share more, so this one will be very much involved in covalent bonding. In fact, all of these are for the most part, not always oxygen. But most of these are going to want to share electrons in order to have a complete outer shell, a complete octet. Up here, hydrogen, it could either share covalently, we're going to find out in water, or it could ionize. It could just get rid of its 1 electron and have just a single positive charge, which we're going to see that a lot, where hydrogen is really just a proton all by itself. You're going to see this symbol quite a bit, well, where it's the ion of hydrogen, and really it's just a single proton. That's it. So let's move on a bit and go back to the periodic table and periodic law. And when I say periodic law, the chemical properties of an element are dependent on the number of valence electrons present. And so when we look at the periodic table again, we're going to go back to it. It's arranged in rows and columns known as periods and groups. And so when we look at each group, we look at the columns, okay, those represent elements with the same number of valence electrons. So when we look at that table, once again, the periodic properties of elements, they wish to gain or lose valence electrons in order to achieve a stable octet. Kind of hard to see my red underline here. Possessed by an inert or noble gas. I'll get to that in a second when we look back at the periodic table. When we go left to right, electrons are added one at a time on the periodic table. The outermost experience an increased amount of nuclear attraction, becoming closer and more tightly bound to the nucleus. And down a column, the outermost electrons are bound less tightly to the nucleus. So let's look at this. If we imagine periodic tables here, okay, well, let's go up here. This is kind of a version of the periodic table as it relates to how big are these atoms? What's their radius? Okay. Well, if I start here in group number 1, first of all, I want to state that once again, everyone in this group has the same number of valence electrons. So everyone in group 1, I could look at the same thing here. Group 1's here. Group 1 is here, kind of smaller and hard to see here. Here's group 1. They are going to have very similar chemical properties because their chemical properties are based on the number of valence electrons. And even though we get bigger as we go down here, okay, it's more and more shells. Their outermost shells all have 1 electron. As we move to group 2, the second column here, they have 2 electrons in their outermost shell. Then we have 3 electrons, 4 electrons. Once again, we see carbon here. That's going to be important. 5 electrons. There's that nitrogen. 6 electrons in their outermost shell. There's oxygen. Then 7 electrons in their outermost shell. And then here's 8. But wait a minute. I said there's 8. There's my octet that I'm looking for. This column of 8, this group of 8 right here, those are your noble gases. They are happy. And the reason that they're happy, and the reason that they're noble, if you will, is because they have the best of both worlds. They have a complete outer shell, which is what they want first and foremost, and they also have an equal number of protons and electrons, which means they are neutral. All right? So, in many ways, the rest of the periodic table are jealous of these guys because they all want to be like these guys. They all want to have a complete outer shell of electrons. And most of the time, we're going to refer to that as an octet. These guys all want a complete octet. All right? So, these guys are going to want to get closer and closer to being like these guys. Okay, now let's go back to the point of this top part right here, the atomic radii. Notice that as we go from left to right here, technically we're getting denser, we're getting bigger as far as mass. All right, because beryllium has one more proton and typically one more neutron or so, and one more electron than lithium. But as we go left to right, technically the atomic radii gets tighter. And the reason that is, once again, is because we have more protons in the middle and more electrons on the outside, and they're attracting each other, so they're pulling themselves in, right? Whereas out here, this lithium, smaller mass than beryllium, and which is smaller than boron and carbon and so forth, but that outermost shell only has one electron going around it. And so it's not being drawn in real tight yet to that nucleus. So even though from a mass standpoint we get bigger going from left to right, technically the radius, okay, is larger over here because these electrons over here are more loosely bound. Now let's think about that for a second. I just told you that these electrons here are more loosely bound. These guys more on this side of the table are more likely to give up their electrons in order to move down a shell, which is already a complete outer shell, and become an ion, and they're more likely to donate to these guys over here. If we look at fluorine over here, right? Fluorine, it has 7 electrons in its outer shell, right? So we know it from right here. Lithium only has 1. Lithium very much would like to pass its electron over here to fluorine, in which case it would now gain a positive charge and fluorine would now get a negative charge. However, they would both have what they really want first and foremost, a complete outer shell. All right? So now we look at ionization energy, which pretty much goes to what I was just saying. This is the energy required to remove one electron from a gaseous atom or ion. And notice, it might be a little hard to see in this graph, but we can see to remove one electron is actually, for most of this first group right here, pretty low because it's not held on to very tightly. Remember, it's kind of loosely held on with that outer shell. While we move down here, and it's a lot more energy to remove electrons. Electrons don't want to leave these guys. They're tightly bound. We can see they're really tightly bound on here. Electrons would much rather leave these guys and transfer to these guys to create ions. We're going to find out as a general rule, these guys in the middle are more likely going to share, while these guys on the outside, more likely to transfer electrons rather than share electrons. Lastly, we have electronegativity, which is the measurement attraction of an atom has for its electrons in a chemical bond. So the higher increase in electronegativity, the increases its attraction for bonding electrons. So it's kind of very similar to this concept of ionization energy. It's going to go higher electronegativity. All right, it has a higher attraction for electrons up here, while down here we have much lower attraction for its outermost electrons. So kind of the same idea here as far as ionization energy. These go kind of hand in hand, and we kind of see the same concept up here. We can see that these electrons, even though there's more of them in fluorine than there is in lithium, they're being tightly held onto, and that's why the radii is smaller, the radius is smaller. So we have 3 different concepts, but they're all somewhat interrelated. The main concept being that, once again, these atoms want to have that complete outer shell of electrons. That's what they're really going for. And they would love to be neutral as well, but what's more important is that complete outer shell. Let's go back to those isotopes. I had already mentioned, once again, isotopes are those atoms that have the same number of protons, but a different number of neutrons, right? Well, we can use this to our advantage, and we do quite a bit in biology and in medicine. Because what will happen is radioactive isotopes are useful in dating old objects, but also in bodily imaging bodily organs through x-rays and is also used in killing cancer cells. So what we do is we can inject a person with an isotope and then scan them, and the isotopes will naturally go, those atoms that are radioactive will go to where they normally want to go, and then they will be releasing energy, and then we can scan to find them. And like right here, we're scanning a thyroid gland, which you'll learn later in anatomy and physiology, but the isotopes didn't make it here, which tells us for some reason there's something wrong with the organ here. There's a missing part of the organ, a dead part of the organ. Something's going wrong here. So that's how radioactive isotopes are used in medical imaging. But while it can be useful, we have to remember also that especially long-term or high doses of radiation can be harmful and damaging to the cells, mostly because they do affect the actual DNA. It can actually cause cancer potentially. So it can be very useful, but also potentially very damaging. And that's where I want to leave it for now before we jump more into molecular bonding, which is going to pick up where we left off here, talking about ionic and covalent bonds.